In today's lesson, we shall be looking at a new method that can be used to solve a first-order linear partial differential equation. A new method that can be used to solve what? A first-order linear partial differential equation. And this method is called the change of variable. It's called what? Change of variable. This is what we'll be looking at in today's lesson. If today is your first time seeing my video and you've not subscribed to the channel, can I hit on the subscribe button for me? So let's get started. Now the change of variable approach, it can be used to solve a first order PDE with constant coefficients, and then it can also be used to solve a first order linear PDE with variable coefficients. So in today's lesson particularly, we shall be looking at what equation that involves constant coefficient. A linear PDE with what? Constant coefficient. Now, all along in our previous lesson, we have been making use of what? The dependent variable u, which is what? A function of x and y. The dependent variable u or the unknown function u is expressed in terms of what? X and then y. Under the change of variable, as the name implies, change of variable, we are going to introduce a new variable to replace the independent variable x and then y. And these new variables that we are going to introduce are called the xi and then eta. They are called the xi and then the eta. Xi, eta, xi, eta. Now the symbol for xi is, and then the symbol for eta, so we have xi, eta, xi, eta, xi, eta. We'll be making use of these symbols frequently in our subsequent lessons, so please get used to them. The name is what? Xi and then eta. Very, very easy and then simple. So as I said, these new variables that we are going to introduce, we are going to use it to replace what? X and then y. So we have our u of xi and then eta. So it means that u is a function of what? Xi and then eta. Now these xi and eta are also function of what? X and then y. So xi and eta are function of x and then y, and then eta is also a function of what? X and then y. So with this, we can write it as what? The dependent variable u is a function of xi. Xi is also a function of x and then y. The dependent variable u is a function of eta. Eta is also a function of what? X and then y. Very, very easy and then simple. What you must know is that with the change of variable, we are going to change the independent variable from what? X and y to what? Xi, eta. And we have done it. Now with the xi and eta, we have an expression for xi, and then we also have an expression for eta, of which we are going to make use of it frequently under this particular method. So with the xi, it is given as s cos alpha plus y sin alpha. That is what the expression for xi. And then eta, it is also given as or defined as minus x sin alpha plus y cos alpha. That is what? Eta. Please take note of this equation or expression very well because we'll be making use of it under this particular method. Now somebody may ask, how do we get alpha? Since we'll be making use of this, how do we get our alpha? Now alpha is given as the tan inverse of b over a. So when you know your a, you know your b. If you take the tan inverse of what? This b over a, it is going to give you the angle. Now how do you get your b? How do you get your a? So let's take it that you have a linear equation of this well form. Let's say 3ux minus 4uy minus 3u is equal to 0. Now this is the first order linear differential equation. From here, our a is the coefficient of us, that is 3. Our b is the coefficient of uy, that is what? Minus 4. So we can obtain the a and b from the equation given. Very, very easy. And once you know them, you take the tan inverse of what? B over a, and that's going to give you the angle. Very, very easy and then simple. Another vital equation that we'll be making use of it under the change of variable is the partial derivative of the function u with respect to x, and then the partial derivative of the function u with respect to y. Take note or remember that the function u is what? Is expressed in terms of what? Xi and then eta. In other words, the dependent variable u is a function of xi and then eta. And xi is a function of what? X and then y. So to find the first partial derivative of the function u with respect to x, we have to go through xi before we get to x. Very, very easy. We can do that using the chain rule to find the partial derivative of this function with respect to x. So when you do that, you are going to get u xi x plus u eta x, that is with respect to x, and then with respect to y, we have u xi y plus u eta y. You can use the chain rule to get this. We can also use a very easy method for us to arrive at this equation. Let me help you with that. So we are saying that the dependent variable u is a function of what? Xi and then eta. Or the function u, unknown function u, is what? Is in terms of xi and then eta. So this is our unknown function u, and it is in terms of what? Xi and then eta. And this xi and eta are also expressed in terms of what? X and y. So it means that xi is also expressed in terms of what? X and then y. And then eta is also expressed in terms of what? X and then y. So we have x, y. Eta is also expressed in terms of what? X, y. Let me use the red ink for that. X and then y. So this is how we get the partial derivative with respect to x. We read it like this. U xi, so we are starting with ux. This one. So we have u xi, then we write u xi, then we have xi x. So we have xi x because we are taking the derivative with respect to what? X. Now we are done. We move on to what? This side because we have an x here. So that we are going to move in this way. We have u eta. So we have u eta. Then we have what? Eta x. Eta x. We are taking the partial derivative with respect to x. Now we are done with x. Let's move towards y. So with uy, so this is our y. So we are going to move in this way. We have u eta. So we have u xi. So we have u xi, and then we have xi y. They move to this way. Xi y. They move on to this side because we have a y here. So we move in this way. We have u eta, then we have what? Eta y. Eta y. So this is how we get this equation because these equations are very important. This equation is going to reduce the partial differential equation into an ordinary differential equation. Is going to reduce or convert the equation which is given in partial differential equation form to an ordinary differential equation, and then we take it from there. Very, very easy and then simple. Now that we know all of these important things, let's look at the steps that is going to help us. So a first order linear PDE using the method of change of variables, we are looking at what? Constant coefficient. So let's look at the steps. First step says that identify the coefficient of ux and then uy. So first we identify the coefficient of ux and then uy, and then I find an expression for xi and then eta. So in finding an expression for xi and eta, we are going to use this equation, and that's going to give us xi and then eta. And then the third step says that we find an expression for ux and then uy. So with that, we are going to make use of this equation to give us the expression for ux, and this one, the expression for uy. Or we are going to make use of this to give us the expression for ux and then uy. Now, once you know the expression for ux and then uy, we substitute ux and uy into the equation that was given. So the equation that will be given, you substitute the expression for us and the uy into that equation, and then you simplify and then you integrate, and then return the original variables to original variable, that is use that times what u x y. Since we introduce a new variable that is in terms of xi and eta, we are going to go back to the original variables, that is x and then y. So these are the steps that is going to help us to find a general solution to a first order linear PDE using the change of variable. So let's take examples. So let's look at our first example. We want to find the general solution for this first order linear PDE with constant coefficient using the change of variable method. So in doing that, we are going to use these steps to help us find the general solution to this partial differential equation given. We are going to go through the steps, we are going to use these steps, we are going to apply these steps to help us solve it. So the first step says what? You should identify the coefficient of ux and then uy. So from the PDE that is given, our coefficient of ux is what? Our coefficient of ux is 1, so our a is equal to 1. Then the coefficient of uy is also 1. Very, very easy. Now once you have this, you find your alpha. And we know that alpha is given as what? Tan alpha is equal to what? B all over a. So from here you can say that tan alpha is equal to, our b is 1, so we have 1 all over what? 1. So our alpha is given as what? Tan inverse of what? 1. And that is going to give us what? 45 degrees. You can convert it to radians, okay? You can also leave it in degrees. So we have 45 degrees. Now once you know this, what do you do again? The second step says that find an expression for xi and then eta. And we know the equation for xi and the equation for eta. So we know that xi is given as what? X cos alpha plus y sin what? Alpha. So it means that we have to find cos alpha and then sin alpha. So from here you can say that cos alpha is equal to what? Cos 45. And when you point cos 45 on your calculator, you are going to get root 2 all over what? 2. And then when you point sin alpha on your sin 45 on your calculator, you're also going to get what? Root 2 all over 2. Now once you know this, you are just going to plug this in place of cos alpha and then what? Sin alpha. So we have our xi. So cos alpha we had root 2, so we have root 2 all over 2, and then we have x. Then plus sin alpha 2 we had root 2 all over 2, and then we had what? Y. So this is the equation for what? Xi. Then move on to what? Eta. Move on to eta. So with eta 2, we are going to have negative sin alpha plus y cos alpha. So we have our eta to be equal to negative sin alpha. We had what? This. So we have root 2 all over 2 x. We have an x here. Then we have cos alpha 2 root 2 all over 2 y. So these are what? The expression for xi and then eta. So this is xi. Let me take it so that you can see it well. So once we are done with this, what we are going to do is we find the partial derivative of xi with respect to x. So this is xi. We are going to take the partial derivative of this whole function with respect to what? X. So it means we are going to differentiate this with respect to x. So when we differentiate root 2 over 2x, we are going to get root 2 over 2. We are differentiating root 2 over 2x with respect to what? X. So we are going to get what? Root 2 all over 2. Because when we differentiate x with respect to x, we get 1. 1 times root 2 over 2 gives us that. Then we move on to root 2 over 2y. Since we are differentiating with respect to x, any function of y becomes a constant. And whenever we differentiate a constant, we get what? 0. So the whole of this is going to give us 0. So we are done with it. Then we find the partial derivative of xi with respect to what? Y. So it means we are going to differentiate xi with respect to y. Since we are differentiating with respect to y, any function of x becomes a constant. And whenever we differentiate a constant, we get what? 0. So 0 times root 2 over 2 gives us 0. We are left with this. Now when we differentiate y with respect to y, we get what? 1. 1 times root 2 over 2 gives us root 2 over 2. Then we move on to eta. So eta 2, we are going to take it with respect to x. So we are differentiating this equation with respect to x. Any function of y becomes a constant. So this will give us 0. And then when we differentiate x with respect to x, we get 1. 1 times negative root 2 over 2 gives us negative root 2 over 2. We have negative root 2 all over 2. Then we have eta y. When we differentiate this function with respect to y, any function of x becomes a constant. So this will give us 0. This will give us what? Root 2 all over 2. Very, very easy and then simple. Now once we are done, we move on to the third steps. What does it say? Find an expression for ux and then uy. So we know that our ux, so we have, is given as u xi x plus u eta x. So let's finish with what? Ux. Now you know xi x, so this is xi x, we are just going to plug in that. So we have root 2 all over 2 u xi. Then we have plus. We also know eta x, so this is eta x. So we are just going to plug in that, and that's going to give us minus root 2 all over 2 u eta. So we are done with what? Ux. Then we move on to what? Uy. And we know that the partial derivative of the function u with respect to y is given as what? U xi y plus u eta y. Very, very interesting. Very, very interesting. Already we know xi y and then eta y. Where is xi y? This is xi y and this is eta y. We are just going to plug in into this equation. So we have root 2 over 2 u xi plus eta y2, we have root 2 all over 2 u eta. So we are done with that. So we are done with the third step. We have the expression for ux and then the expression for what? Uy. Now what do you do again? Substitute ux and then uy into the equation that was given. So the equation that was given is this one. We are just going to plug in ux and then uy into the equation that was given. So that is the fourth step. So we have fourth step. So the equation that was given is what? Let me use this so that you can identify them. Ux plus uy minus 2u is equal to 0. So we are just going to plug in ux and then what? Uy. So ux we have root 2 over 2 u xi minus root 2 over 2 u eta. Then we have plus uy. So this is uy root 2 over 2 u xi plus root 2 over 2 u eta minus what? 2u is equal to what? 0. Now from here you can see that some of the terms can cancel themselves. you can see that root 2 over 2 u eta can cancel root 2 over 2 u eta. So at the end, we are left with what? Root 2 over 2 u Zaya plus root 2 over 2 u Zaya minus 2u is equal to 0. Very, very interesting. Now the next step says that simplify and then integrate. So let's simplify this and then we integrate. So we have this plus this will give us what? 2 root 2 all over 2 u Zaya minus what? 2u is equal to 0. This will cancel this. We are left with what? Root 2 u Zaya. Now let's send this to the right hand side to give us what? 2u. Now from here, yes, let's divide both sides of the equation by root 2 and then we divide both sides of the equation by u. We are separating the variables. So we are going to have u Zaya all over u is equal to 2 all over root 2. Very, very interesting. Now we know that u Zaya can be written as what? Del u del Zaya. The partial derivative of u with respect to what? Zaya. Because if we have ux, we can write it as what? The partial derivative of the function u with respect to what? X. That is del u del x. Under the notation for PDE, we came across this. So we are going to write u Zaya in the form of what? This. Good. So we can write this as 1 over u del Zaya. Is equal to what? 2 root 2. Now from here, we can write this as 1 over u del u is equal to, we are multiplying both sides of the equation by del Zaya. So we have del Zaya. So we are still on the simplification. So we can write this as del u all over u is equal to 2 all over root 2 over 2 del Zaya. Very, very easy. Now we've separated the variables into u and then Zaya. So we can what? Integrate. Very, very easy. So we integrate both sides. Now when we integrate del u over u, we are going to the length of the function u, because we can write this as the integral of 1 over u del u. We have a function and a derivative, and whenever you have a function and a derivative, it gives us what? The length of that function. So we have ln u. Now when we integrate 2 over root 2, we are getting 2 over root 2, and then we have what? Zaya. The same thing applies, the same thing when you have, let's say, the integral of dx. When you integrate dx, what do you get? You get x. So when we are integrating del Zaya, what do we get? We get Zaya. So that is why we have added to it, because we have a constant in front. Then we add our constant of integration, c. But remember that the independent variables here that we are dealing with are what? The Zaya and then eta. But what? Zaya, any function of eta becomes what? A constant. So this constant is going to be a function of what? Eta. But I realize that we have length here. So let's take the length on the constant as well, so that we can clear the length from the equation to make it easy and then simple. So here is going to be length of what? Length of a function of what? Eta. A function of eta. Very, very easy. Let's continue from this side. Now from here, we can start to bring this to the left hand side. So we are going to have ln u minus what? Length of a function of eta. And that is equal to what? 2 all over root 2 and then what? Zaya. Apply our basic knowledge in logarithm. Since we have length and length, we can decide to pick one of the length, since they are subtracting, we divide their argument. And this is equal to what? Let's clear the length from the equation by taking the e on either side of the equation so that the u cancel the length. So we have this will cancel this. We are left with what? U all over a function of what? Eta I is equal to 2 all over e exponent 2 all over root 2 and then Zaya. Very easy. We want to make u the subject, that's the unknown function that we are looking for. So we can say that our u, remember that this u is in terms of what? Zaya and then eta. So we have Zaya and then what? Eta. And you can see it clear from the equation. We have Zaya and then eta. So we have a function of what? Eta multiplying e exponent 2 all over root 2 Zaya. Very easy and then simple. So this would have been the general solution. This is the general solution. But I realized that the question was given in terms of x and y. So we have to return back the variable, that is the last step. Return the variables from u Zaya eta to x and then y. So at this very point, we are going to return back to the original variables. That's what x and then y, because we have Zaya eta. We want to get the general solution in this very form, u at x and then y. This is what we want to have. But we have Zaya eta, so we have to bring our x and y back. How do we bring it back? That's a very nice question. How do we bring it back? So with the Zaya, we gave an expression for Zaya, if you remember. We said that our Zaya is equal to what? Root 2 over 2 x plus root 2 over 2 what? Y. This is the expression for what? Zaya, the one that we looked for. And then eta, you also give an expression for eta as negative root 2 over 2x plus root 2 over 2y. So these are the expression for Zaya and eta. So wherever we see Zaya and eta in this general solution, we are going to plug in this. So let's start with Zaya. So we know that Zaya is what? Root 2 over 2x plus root 2 over 2y. Now we can simplify this, right, to make it smaller. So with this, we can write it as root 2x plus root 2y all over 2. Since the denominators are the same, we can write it as that. And since we have root 2 here, we can bring root 2 right. So we have root 2, we are left with what? X plus y. And all of this is over 2. Very, you can also write it like this. Now root 2 over 2, we can rationalize the numerator. We can write it as root 2 times root 2 all over 2 times what? Root 2. We are rationalizing the numerator. And this is going to give us what? 2 all over 2 root 2. This will cancel this. We have what? 1 over root 2. Very interesting. In fact, math is very interesting. So it means that root 2 over 2, we are going to write 1 over what? Root 2. So we have x plus y all over root 2. Very interesting. Now let's move on to the eta. Where is my Burumaka? So we have eta. So you know that eta is also giving us minus root 2 over 2 plus root 2 over 2y. Now since they are of the same numbers, root 2 over 2x, just that one of them is minus. So we are going to have our eta to be in this real form, y minus x all over what? Root 2, because the only difference is minus. And the minus is on what? X. So we have minus x. So once we have this, we are just going to plug this into the general solution. So we have our u. Now our independent variables are what? X and then y. So let's use okay, we have x and then y is equal to, we have a function of what? A function of eta, and we know that eta is written as y minus x all over root 2. And then we have y exponent 2 all over root 2 multiplying Zaya. And Zaya, this is Zaya, is also giving us x plus y all over what? Root 2. Very, very interesting. Now with this, we can just simplify it small. We can just what? Simplify it. Very, very interesting. So finally, we have our u xy is equal to a function of y minus x root 2, and then we have y exponent. When you do the algebra, I think 2 over root 2 and then root 2 will go away y, because 2 all over root 2 times 1 over root 2, when you do your rationalization, this will give us 1. So this is what we have. So at the end, our general solution is given as what? Is given as this. So this is our general solution. Very, very easy and then simple. See you tomorrow on another example on change of variable. Bye bye.